Hi, my name is Tina, and I'm going to be talking a little bit about gates. This first section is what gates are and what combinational logic is. Okay. And when what I think is important about gates is knowing their name, knowing their truth table, knowing their symbol, and notation, kind of the mathematical notation. And of course, talk to Dr. Benson. She will have maybe her own requirements. But gate name, there's various different kinds of gates, some called and, some called or, some called nor, some called nan. And then you have a table that tells you how these different circuits, how these different gates are basically circuits, how they behave. And the symbol is when you're drawing a schematic, in other words, a diagram of a circuit. You use symbols to represent these NAND gates or NOR gates or XOR gates. And knowing that symbol is important so you can draw diagrams and read diagrams. And then notation, mathematical notation. Sometimes you need to figure out a circuit on paper. You need to go through the math, so it's important to know the mathematical notation of that. So let's just, gates are, if you start thinking about gates just in your day-to-day life, they make sense. And I'll just tell you right now, there's a gate called an AND gate. So let's see. Let's see how a gate, an AND gate might work. If I say, is 6 equal to 8 and 7 equal to 9, what do you say? You say no. Okay? 6 isn't equal to 8 and 7 doesn't equal 9. So this is definitely false. Okay? And in digital, I'm guessing that you probably already have talked about zeros and ones. 0 represents false. Okay? It doesn't mean 0 volts. It doesn't mean 12 volts or 15 volts. It doesn't mean 3 volts. It means the 0 is just a representation of false. Okay? When you actually implement it in a circuit, false can be represented by any voltage the designer decides to use as false. Okay. All right, so let's look at this. 6 equal to 8 and 7 equal to 7. So 7 equal to 7, that's true, but this and this have to be true for this whole statement to be true. So is that true? No, it's also false. Okay, over here, 6 equal to 6, oh, that's true. Okay, and oops, no, this one's false. So if I have a true and a false, okay, and we've called false 0, so true is a 1. So this would be, if 6 equal to 6, that's true, so that should be a 1. And if 7 equal to 9, oh, that's a false, that's a 0. So if it's a true and a false, that's still false. Okay, and then you have 6 equal to 6 and 7 equal to 7. Is that true? Is 6 equal to 6 and 7 equal to 7? Yes, that's true. So true is a logic 1. And again, logic 1 doesn't mean 1 volt. Doesn't tell you anything about the electronics. 1 just means, in this notation on paper, that means true. In a circuit, for example, there's a port on some of the older computers and various other devices. I think they're still available in the lab. But a plus 15 volts, actually 3 to 15 volts, I believe, means false for the RS-232 port, and a negative 3 to negative 15 means a true. So it's whatever the designer decides to have represent true or represent false. So this 0 and 1 right here has nothing to do with the electrical properties of your circuit. Okay, but the point of this slide is that, okay, we have this gate named and what it says is, if you put in, thinking electrically now, if you put in the voltage that represents false into one input of this AND gate, and then you, on the other input, so I'll tell you right now that this AND gate takes 2 inputs and gives 1 output. In this case right here, this is an input, whether this is true or false, and the output is this logic 0 or logic 1. Okay, so if you take a circuit, a NAND circuit, and you give one input the voltage that represents false, and gives the other input voltage represents false, your output of that circuit will be false. Whereas if you give the voltage that represents true to your AND circuit or AND gate to one input, and you also give a voltage that represents true to the other input, then the output of that circuit is also 1 or true. Okay. Again, not saying anything about what voltages, your 0 and 1, that just means true or false. Doesn't tell you anything about the circuitry that does this calculation. Okay, let's do some more. Okay, so let's put this into a table. Let's call this A and this B. So if A is false and B is false, then the output is false. If A is false and B is true, then the output is false. A is true, B is false, output is false. If they're both true, the output is 1. This right here, this is a truth table. This is a truth table. This tells the user of that piece of electronics, or that gate, the user of that gate, how that gate behaves. It says if you give me two, if I have an AND gate which has 2 inputs, if I give you 2 false inputs, I'm going to get a false output. So whatever the voltage is for false in, I get the voltage for false out. If I give the voltage for true on both inputs, then I get a voltage true out on the output. Okay, there's your A and B. All right, and here's the symbol for the gate. Remember, there were 4 things that I was going to ask that I think are important to for you to learn. One is the symbol. Well, the name first. The symbol, so then you can draw diagrams using gates. The truth table that describes how the behavior goes, and then the mathematics, and that's not a minus sign there. And means both of these have to be true for the output to be true. And if you think about this in mathematical form, if either A or B is 0, then out is going to be 0. So and looks mathematically, it looks a lot like multiplication. So that's why multiplication sign is used for that out. So this is just that's not a minus sign right there. Okay, so 4 things to remember for this: name, symbol, truth table, and notation, mathematical notation. All of these gates that I'm going to show you, you can have more than one input. So let's see what happens here. Try to make a sentence. If my name is Bartholomew and I'm 8 feet tall and I have 6 toes, is that, I just strung 3 statements together using and. None of them are true. So I'm going to get a false out. But if I say, my name is Tina, I have curly hair, and my desk is a mess, that's a 1 and a 1 and a 1. That's a true, true, true. And the output I get is a true. So here's a truth table. What happens when you have more inputs means that in your truth table, that means that on the left side here, so left side of the truth table are your inputs, right side are your outputs. Okay. When you increase your inputs, what happens is on a truth table, let me backtrack for a second here, all combinations of inputs need to be included on the input side of your truth table. All combinations of inputs. Maybe later on, when you get used to designing, you can skip a row or 2 or 5, but right now, just getting used to this, never ever ever skip a row in your truth table. Okay, so to make sure you get all combinations of possible inputs, I always start from 0, 0, 0 and just count up in binary. So that's 0 in binary, that's 1 in binary, 2, 3 in binary, 4 in binary, 5 in binary, 6 in binary, 7 in binary. So I just count up each row, and when I get to all ones, then I know I have every possible input combination in my truth table. And you know, for an AND gate, there's only one row that has 1. So you could say, oh, gee, I don't need to do that whole table. But again, until you really get used to designing with this, and I would suggest this entire quarter, using complete truth tables, till you get really used to it, don't skip this step. Make sure you have all inputs in your truth table. Okay, and then notation, mathematical notation is just now you're ANDing one more input, so just put another multiplier and see. Okay. Here's something called an inverter. And an inverter just takes, if you put true in, you get false out. If you put false in, you get true out. What that looks like in the truth table is if you put false in, you get true out. If you put true in, you get false out. And the notation, again, sorry about this bar. I guess I should get rid of that. You put a bar over the wire name or the input, and you get out. So it's just a bar. It just represents an inverter in the mathematical. And this is one of the few gates where you only have one input and one output, though you can turn this into multi-wire input if needed, but then just everything's inverted. Okay, so you've seen an inverter and you've seen an AND gate. Okay, there's a number of other gates, and I'm going to go a little faster through them. OR gate, or let's think about OR as a sentence. If I say my name is Tina, or I have 5 noses. Okay, one of those statements is true. Since one of the statements is true, then the whole statement is true, because I'm saying one or the other, and that's what that says here. If one statement's false and one statement's true, then your output's true. If they're both false, like if I say I'm 8 feet tall and I'm Australian, that's false and false, and you get a false out. But if either one of the statements are true, then your output is true. And the notation here is if either one of them is non-zero, then your output is non-zero. And if you remember in C programming, anything that's non-zero is counted as true, for those of you who remember C. Okay, and just as with the AND gate, you can put as many inputs as you want, but note that when you add a single input, it doubles the number of rows in your truth table. Okay. Again, you want to have a row for each possible combination of inputs. So, and to do that, it's good to start counting from 0 and count 1, 2, 3, 4. Okay. XOR gate, or if A and or B were true, then the output was true. But XOR means that only one of the inputs can be 1. The other one has to be 0. Okay. This is for a 2-input gate, input XOR gate. So right here, both of them are 0, so you get 0. Both of them are 1, you get 0. Only 1, 1 here, only 1, 1 here, so it's true. It's one or the other. Okay. And the symbol for that is a little plus inside a circle. And this is just the equation for it. Here's the actual notation. Here's what that actually means. Okay. And the next question I usually ask when I'm doing the class is, okay, well, what if you have, for the OR gate and the AND gate, I just put more inputs on it, and you could figure out what that meant. What about if I have, let's see, 1, 2, 3, 4, 5, 6 inputs to an XOR gate? So I think I have a picture. No, I don't. Nope. Okay. Well, let's say I had 3 inputs to an XOR gate. When is that true? And the actual rule for XOR gates is that an odd number of inputs are 1. So an odd number of 1s right here. That makes the output true. Okay, and all of these gates, you can put a little bubble on the end, and that bubble represents an inverter. If you remember, inverter takes whatever value comes into it and flips it. If a 1 comes into an inverter, then you get a 0 out. If you got a 0 into the inverter, you get a 1 out. Okay, this is like you had an inverter out here and it got eaten by this AND gate, and all that's left is the bubble. Okay, and this is, the technical term is bubble, which I always think is cute. And what that means is it's just your AND gate table, but all the outputs are flipped. This is just like putting an inverter on the output of an AND gate. And in the same way, you just put a bar over. So that is what an AND equation looks like. Just put a bar over it, and there's your NAND equation. And same thing for whether you have 2 inputs or 3 inputs. XNOR or NOR gate, same thing. It's just like there's an inverter on the output, so whatever used to be 0 on your truth table is now 1, and whatever was 1 is now 0. And you put multiple inputs. And I will let Dr. Benson talk about De Morgan. I'm going to go on and talk about designing a little bit. And there's also XNOR, which is your XOR with an inverter on the output. Okay, and De Morgan's, okay, summary of gates. Okay, finally we build a circuit.